Is there a way that you can share and then it can be edited?
Say that again? It's being live streamed. So maybe after, after we can end the recording after, and then we get into the stories.
Oh yeah, that's interesting. Yeah.
Yeah.
So I'll be ready just whenever you want me to start. Just let me know.
All right.
I will say though that so I'm a little bit late to this because I was in a meeting. I think meeting ran for like almost 2 hours. Can you believe that? 2 hour meeting. And on today when I wanted to get everything prepped. So this workshop is or this talk is very like demo heavy because I like to show people things. But because of that meeting, it means I've not had a chance to test the demos. So let's hope that that things don't break partway through. If things break, just take my word for it that it worked once upon a time.
Don't worry, the demo gods won't be with you.
So last time I gave this workshop, it was in person, but one of the demos did like badly break, and that was the first time I've ever had a demo break on me. So
the first time.
Yeah, and I love doing demos. Like almost every talk I do, I put loads of demos in, and just that one time.
I need to talk to your God. Or the person, or your heavenly being, because me, every single time I try presenting, demo gods usually catch me.
I know it's I don't know what it is. Maybe they like me. I was watching someone else give a talk once, and like all his demos broke. And he was like there on the stage, nothing was working. I was just looking at him like, oh man, poor dude.
Oh man, that was hurtful.
Yeah, like secondhand embarrassment.
And the worst thing is maybe the demos will maybe share the information properly and then it doesn't work. And you're like, oh, okay. So exactly. I'm sorry.
But I will still just caveat that if things break, then don't look too bad on me. It's as I said, I didn't get a chance to test things, but hopefully it should work. I mean, I've done this stuff quite a lot.
Yeah. Well, no problem. We're looking forward to it, Jay, and hoping that it will work. We know it will work. Yeah. So I think we can begin. I can do a small intro. Thank you everyone for joining us. I know a few more people will join because we had said we'll start a bit late today. So today we have Jay Harris, and he's a penetration tester and a hacker who's based in the UK, and he runs two companies there, one called Digital Interruption and RexScan, that's the second one. And where I met him was on a YouTube video, and it was, I think, he had shared something about being the founder of Manchester Grey Hats. So I joined the Slack channel. That was like 3 years ago. And anyone who wants to join, you can join that as well. So yeah, today we have Jay Harris on the session, and he'll be taking us through hacking radio signals with low-cost software-defined radio. Welcome, Jay.
Thank you very much. So are we ready for me to begin?
Yes.
Okay. Before we do that, I just do want to ask, is anyone familiar with SDR, software-defined radio? Or is this a new topic for people?
Some of us are here to learn.
Okay. So a few people have seen it. Okay, cool. So we're going to go through like quite a few different things. Maybe some of it is parts you've seen before. Hopefully there'll be some new stuff. If people do have questions, just either come off mute and ask me or type a message in chat. I will try and keep an eye on the chat window, but sometimes it's difficult with everything going on. I also let people know that the setup that I'm using, I'm presenting from one machine, but I tend to do my demos on a separate machine. So on a Linux machine, I tend to prefer for SDR stuff. So I'm remoting into that other machine, and you'll see that. I'll make it clear when I switch over, just so people can kind of know what I'm doing. So yeah, as we said, today we're going to be looking at SDR, software-defined radio, and how we can use that to attack like wireless and radio systems. So this is the type of thing. Oh, has my screen? Are my slides updating?
No.
They're not. Okay, it didn't look like it was. Not did it even manage to get the demo before things broke? Okay, we might need to do this another way. Maybe maybe it's best if I just share the screen as opposed to. Let's try it this way. Okay, can you see the slides?
Yes.
Yeah, okay. So this is what got me into SDR really. Oh, sorry, which screen are you seeing? Which slide are you seeing?
Pacemakers and implantable cardiac.
Okay, awesome,
yeah.
Fantastic. Okay, and I think it's still, okay. So yeah, this is what got me into SDR. I heard stories about people with electronic pacemakers in, and I heard how sometimes they were vulnerable to attacks. And when I started researching this, I realized that how easy it was for somebody to attack some of these pacemakers. So a lot of these things, like pacemakers, cardiac defibrillators, these are systems that get embedded into someone's body, by their heart usually. And the idea that you could take control over those by sending them radio signals, just, to me seemed absolutely fascinating. The fact that you could almost walk around just spraying like these radio signals out and they would have that kind of real world impact. And so by reading about some of these attacks, kind of opened my mind to, this whole concept of SDR. And the more you look into it, the more you realize how radio is used, right? So even if you take a car, right, just a standard car, you might think that the only radio in that machine is the radio that you listen to when you're driving down the street. But actually, think about the key, like the key fob, how you unlock your car with a controller. In the tires, they have radio systems that supply information about the tire pressure. They have like parts that control the engine all through radio. So even something like this, once you start looking into it and looking at how radios are actually used, it is a massive world of things that we do want to start to perform assessments on, and with the right tooling that opens up to us. So as an example here, somebody was able to hack one of the cars to be able to display different messages on the dashboard here, by, again, taking control of some of the radio systems on the device. Other people have been able to do things like take control of the braking and again, like affect the speedometer here. So yeah, like all these things that kind of really open up to you once you start learning more about SDR. And I think another really, really good example of something that is, radio based, but not necessarily as obvious as a radio system, is some of these attacks such as Van Eck phreaking, or Tempest. So this is where it can be possible to pick up those unintentional transmissions from devices, right? So electronic devices, they will transmit radio frequencies inadvertently as electronics are being used. So the data that's transmitting through the cable between a computer and the monitor will transmit some radio signals. And with low-cost SDR, we're able to receive that and decode it and pick up the picture that is being sent down that cable from across the room. This was something that I thought was, only theoretical, like, oh, there's no way that would actually work, or it wouldn't work with modern day devices. But it does. A year or so ago, I was actually playing with some software that let you do this with SDR. So I had my monitor, and I had my SDR, which I will show later, but I had my SDR, a few inches away from that monitor. And I was able to use the antenna to pick up those radio signals and then convert them back into a picture of what was on the screen. If people are interested, there is a write-up on my blog about like how I did that. So yeah, again, I thought this was purely like theoretical or only in the realms of, you know, government agencies, but actually with some of these devices, it becomes something that you know, we can add into our bag of tricks, you know, things that we can do on pen tests. So then just very quickly, these are old slides, by the way. Our design has changed a lot since then, but my name's Jamel, or most people call me Jay. I'm a pen tester at Digital Interruption. Also started RecScan earlier this year. RecScan, we do like mobile, like Android vulnerability scanning software. My interest really is like mobile and radio and reverse engineering. Here are some Twitter accounts that you might want to follow. Manchester Grey Hats is a group that I set up in Manchester. I run workshops very similar to this kind of workshop. Normally, you know, before COVID, we were doing them in person and trying to live stream them as well. Since COVID happens, we kind of changed how we do things. But, you know, we have a Slack channel. People are more than welcome to join. If people want to get involved with, you know, some kind of, you know, hacking group, then please join us. You know, it's really a way for me to teach people how to do things kind of safely and securely and legally as well. So this talk, yeah, as I mentioned, there'll be more of an introduction to SDR, but we will be looking at how we actually attack radio signals, some of the different attacks that we can perform. And then we'll move on to looking at how we can actually identify radio signals, because it's one thing to be able to just perform common attacks, but if we actually want to understand what data is being transmitted over the air, then we need to be able to understand how to kind of break that down and look at it. And then if there's time, we might look at some attacks that are in common wireless protocols. So you know, things like GSM, for example, or Bluetooth, and understand some of the security implications around that. As I mentioned, please, if anyone has any questions, feel free to just type them or come off mute and say them. I might need somebody to just let me know if there is a question waiting though. So yeah, let's just start, I guess, introduction to SDR. So this diagram here is something I put together that kind of shows, at least in my mind, what a radio is, right? A hardware radio. So it will have several components, antenna, obviously. It will have certain filters, so they will receive you know, data from the air, and it will filter for certain frequencies and things like that. It will go through different, you know, components, let you tune into the correct frequency, and then eventually it will do some kind of demodulation. And this is where it takes the radio signal that's coming through the air and turns it back into data. So if we think about the case of a you know, FM radio, that's going to have an antenna, it's going to take in those, you know, radio signals, it's going to process them, it'll come through the demodulator, and then we will get noise out of the speaker on the other end. Now these are obviously very like common, like hardware radios are common. They're very cheap to produce. You know, in the UK, at least I can go into a pound shop, which is, you know, just like a shop with loads of, you know, junk that you can buy for £1. And I can pick up a little radio that I can listen to. You know, they cost hardly anything. But a radio is only ever going to do one thing. So a hardware radio is only ever going to be able to tune into those signals that it was supposed to do. So, you know, if you take a phone, for example, your phone will have a radio chip for Wi-Fi, a radio chip for Bluetooth, a radio chip for, you know, 4G or 5G. But those chips are only ever going to do those one thing. A Wi-Fi chip is only going to be able to listen to Wi-Fi. Now, SDR, on the other hand, is a bit more like this. You have your antenna, the part that you're able to take signals from the air, and it goes through an analog to digital converter. All the demodulation, all the other components that that we were seeing in that first diagram are instead sent to software. So the demodulation, for example, is now happening in software. So what this means is that the radio will do whatever the software lets that radio do. Of course, they're going to be more expensive to have an SDR, but you have a lot more flexibility in the types of signals that you can like play with and tune into. Now, I like to think of this in a way of well, when I was younger, when I was listening to the radio, I was always curious what happened if I could tune up the end of the dial, and I would keep trying to go up as high as it could go, and I'd always be disappointed when I couldn't get it past the end of it. But with SDR, you are able to do that. You're able to tune into more frequencies and see what else is kind of happening in the air. So yeah, they're a lot more general purpose, but they are more tied into like the software. If the software allows the device to do something, you can do it. So for example, I can have an SDR, and if I have the correct software, that will work as an FM radio. If I change the software, it could work as a Wi-Fi card. So it's all happening in software. And so when it comes to like security testing, we can use this to really start to analyze wireless protocols in a way that we wouldn't necessarily be able to do before. And then of course it works in the opposite as well in a lot of cases. So you'd have your software that sends data out to the antenna, which then goes out into the world. So there are a few different types of SDRs at different price points. So I guess we'll start on the right hand side first, but with this one is the RTL SDR, which I did have one on my desk over here. So that's something like this. If people can see, I'm not sure if they can see me, but very low cost SDR. These ones are actually interesting because they started out really as a TV tuner, right? So people are using them to watch TV on their laptops, their computers, etc. And somebody realized that how these worked is they were taking in the radio signals, and then in the software, it was doing the demodulation. And they realized that actually if they changed that software, they would be able to use something like this to tune into different signals, right? So these are the lowest cost SDRs that you can get. These costs about maybe £10. I don't know what that is in other currencies, I'm afraid, but around £10. And you can get them off Amazon fairly easily, at least I can in the UK. Now there are some limitations that it will only tune between a certain band of frequencies, so 24 megahertz to 1.7 gigahertz, which is actually quite a wide spectrum that it can do. It can tune into to loads of like common devices, especially common like low cost IoT devices. So it can be interesting for that. It can go into it can pick up a 2 megahertz band at a time, and can listen to data at about 2.5 mega samples per second, which is is a lot of data, but again, it's just a small device, so it can't look at a massive spectrum at one go. Now, the other big limitation of these devices is that it's receive only, right? So it can only receive data. Some of the other devices can transmit data as well. The HackRF is my favorite one to use. That looks like this. If people can see my video. This is, are people able to see me, or should I stop sharing my screen?
We can see you.
You can
kind of see me. Okay, so this is the HackRF. This is slightly more expensive, but still relatively cheap. For perspective, before SDR was really common, devices would cost tens of thousands of pounds, and now they're down to a few £100s. I like the HackRF because it's open source software and hardware. So if you want, you can get the schematics and try to build one yourself. The bandwidth, I think, is a good amount. And that is tied to the sample rate. It can receive a lot of data in one go, which means you're able to have more data to process. That can be challenging when you're doing things like in virtual machines, for example. So it's kind of difficult to take that much data and push it through like USB to a virtual machine. So that is something to keep in account. When we're talking about 20 million samples a second, that is a significant amount of data. But it can tune between 30 megahertz and 6 gigahertz, so a massive range. I rarely need to go outside of those things, to be honest. For perspective, like Wi-Fi is 2.4 gigahertz. This can go all the way up to 6 gigahertz. It can actually do beyond that if you're willing to sacrifice some accuracy and stuff. And it can transmit, but it can only transmit or receive at one time. For me, that's no problem. The type of stuff that I look at, it's okay for me to just receive data and then transmit it differently. You can use 2 HackRFs if you want. At that point, though, you may as well look at some more like larger systems like the USRP. This is a kind of more like, I guess, pro device that lets you add to it. The cost can change depending on the types of model that you have and the deltables that you have in it, but that will be full duplex. And with that kind of device, you can do things like emulate a cell phone tower and do like lots of things that require kind of two-way communication. Obviously, the sample rate is a lot higher, and the bandwidth as well. So what what can we really look at, right, with these devices with SDR? Now, obviously, the whole this whole spectrum of light, which really is what radio waves are, is massive, and really with SDR, we're kind of looking at things in kind of like in some of these ranges on the left. You probably can't see my mouse as I'm highlighting it, but some of the obviously visible light, we're not looking as high as that, but it's like the radio, TV areas and stuff. And within that spectrum, there's tons and tons and tons of stuff. Again, lots of IoT devices will be using things that we can tune into with SDR, FM radio. I know this isn't an easy diagram to read. The point is not really to read the details on it, but just to see the types of things that are used within some of these spectrums. Some examples, Bluetooth will be working obviously over radio, Zigbee, LTE, GSM, Wi-Fi, like all these kind of common technologies you're going to be familiar with. And with SDR, with the correct software, we're able to perform certain attacks against those systems, either by pretending to be a device on that. So for example, with Zigbee, we can, if we have the right software, we can be a Zigbee client. We can change the software, and all of a sudden we're an LTE base station, or we're able to send data to LTE base stations. And then some other kind of interesting devices, things that I just kind of were able to just find. So obviously like radio cars, obviously radio, walkie-talkies, being able to tune into those with SDR, can be useful. I see a lot of these devices where people are plugging them in to their home, and they plug something into that, and then they use a remote control to enable or disable that device, like lights and things. With SDR, we're able to take over those. I am seeing more people using alarm systems as well, which is kind of interesting, where they are buying kind of like these low-cost wireless alarm systems just from from Amazon, from the shops, not realizing how insecure they can be. You can argue, if someone takes control of your RC car, not the end of the world. If someone takes control of your alarm system, then that's actually a bit more of an issue. I've seen attacks against cars as well. So mentioned before with cars that use the keyless entry and remotes and stuff. They with SDR, we're able to perform certain attacks against those in order to open those cars. And I have seen criminals utilizing that to actually steal people's cars. Sometimes what they'll do is they'll get an SDR, and with cars with keyless entry. So with keyless entry, you have the key on you, and as you go close to the car, you're then able to open the car door because it knows that the key is close by. But what do most people do when they go home of an evening? They put their keys kind of close to their door, right? There's usually like a bowl or something by the door. They leave their keys there. And so I've seen videos of criminals that will get an SDR, hold one end close to the door, someone's door, have another SDR that is close to the car. It's basically just relaying that signal between the two devices, allowing the car to unlock. Wireless keyboards as well is always a fun one. So with SDR, you're able to tune into those wireless keyboards and basically see the characters going over the air, passwords and things. I find these ones kind of interesting because they do sometimes apply encryption to the key presses, but with the like A will be encrypted the same each time, so you can build up like a table of encrypted key presses. And then the IME is a really interesting thing that maybe I'll talk about later if people are interested, just in terms of time. But this is my favorite story about hackers and SDRs. So I like this quote: "Security won't get better until tools for practical exploration of the attack surface are made available." And that is true. Now that we have these low-cost SDRs, we're able to do a lot more in terms of attacks on these systems to look for some of their weaknesses. So let's try a little demo, and we'll see how well it works. I will need to change what I'm sharing. So let me see if I can do that. See, so I want to share. Yeah. Okay, can people see this this window with the terminal on it?
Yes.
Okay, cool. I had it all set up. I was planning just to press buttons and it automatically changes screens and things, but that didn't work. Not the end of the world. So what we're going to use here is the HackRF. So I've got it attached to my other laptop that's in the corner here, and that's what we're looking at on this. And the first bit of software that I like to use is GQRX. Now this is basically, think of this as like a tuner, right? An FM tuner. As I mentioned before with the radio, how we might be able to like go past the end of the radio to see what else is there. That's what GQRX lets us do. So, but it's a good demonstration of SDR, right? So if I press play, it's now using the SDR to listen to radio waves that are coming through. I'm not sure how easy it is to see, but you have two different views here. At the top is this one view that shows us kind of where a strong signal is. And then at the bottom, this other view that is more like over time. So it shows us where a signal is over time. So the FFT and the waterfall at the bottom. So if we move over to here, I'm not sure how easy that is for people to hear. All right, can people hear that? Did anyone hear that?
Yes.
Yeah. Okay. So we're using this software to turn the SDR, the HackRF, into an FM receiver. So it's receiving FM radio signal. So this is just a UK radio station. All right. So we're now able to just like tune through. And what we can do, as I mentioned, is we can just keep going up and up and up. And we see what's going on. Sometimes you'll see things like walkie-talkies. One time I was at a friend's place and we were playing through and I heard their neighbor. Don't know why. Maybe they had a baby monitor in their room. Maybe they were using like some kind of headset or something, but we can only hear one side of a conversation. So it was a little bit weird. You know, you can pick up all kinds of things. And if we keep going up, we can see things like this is probably a good example. It might be difficult to hear. Let's see. So this, instead of it being a analog transmission, this is a digital transmission, right? So yeah, unfortunately, it's not super easy to hear, but you can almost hear the bits going over the air, like the ones and zeros, because it's just this very like digital sound. And what we can do, again, if we change the software, we can then start to demodulate that and see what it's doing. I won't do that now because that is, I know what these signals are. They're POXAG, which is the like paging network. I don't know if people are familiar with like pages and stuff, but those are digital transmissions, and you can tune into those with the SDR. And with some software called Multimon, you can, if you would run something like that. Again, I won't do that. There are laws that say that we're not able to like decode some of these things and retransmit them over like the internet. So I won't do that here. But if you were to run a command such as this and have GQRX feed that data into that software, then again, the software is changing and it's able to demodulate that, turn those ones and zeros over the air into basically, you know, clear text messages. As another example, people can use this to tune into like aircraft. As aircraft fly by, they do transmit their location, right? Their location, their longitude, latitude, and things like, and some other like identifiers. And with SDR, you're able to tune into that and decode that and you know, put it on a map and things like that. It's kind of a fun thing to do if you've not done it before. So yeah, first demo, that worked okay. I'm kind of glad with that. So does anyone have any questions while I just take a drink of water? Okay, awesome. So I hope that makes sense, right? But yeah, we're able to use different software to receive those signals and do different things. And here we're using GQRX that works as a like FM and AM demodulator, so to turn it back into audio, but also we're able to tune into other things. So just out of curiosity, I'm going to go up to 2.4 gigahertz. So this will be like Wi-Fi, right? So you can see all these lines coming across here. That is it picking up likely Wi-Fi signals, maybe even the data from this, you know, this stream of some connected to a Wi-Fi network, picking this up. Now the software, GQRX, doesn't know how to demodulate that, but it can display it to us. Then if we created some other software, we'd be able to like view those raw packets through the air. Okay. So let me try and get back to my slides. Okay. So I think my slides are here now. So what kind of attacks are we actually doing on these things, right? So my favorite one to do is a replay attack. So this one, very basic. Somebody is there, they do something on a radio. So in this case, imagine a garage door. They press a button to open up their garage door or open their car or something like that. And their like button is transmitting a radio signal. And that is being picked up, and the door is opening. I will just confirm people can see my slides, yeah? Presumably people can see my slides.
It's visible.
Okay. Just it's not easy for me to like see all the stuff that's going on and whether the slides are coming up. But yeah, so as an attacker, what we can do is we can use SDR to receive that system, like that signal, right? And record it basically. Then another time we can go by and we can replay that signal and the door will open. Even if the signal is encrypted, sometimes that doesn't matter. If there is like, if the encryption is the same each time, then it doesn't matter whether it's encrypted, because we don't need to decrypt it. We don't need to like read the data. All we need to do is just say like, hey, this is the open door command. And that was a problem with some devices where it is encrypted, but it's encrypted the same time each way. There are some protections against this that are particularly interesting. You can have like rolling codes and things, but there are attacks against rolling codes. So there's some pretty good talks about that by Sami Kamkar. Tells you how to try and attack some rolling codes. Another one, I kind of just say like data recovery, but this is just tuning into data that's unencrypted and being able to decode it and read it. I mentioned before Tempest or VANEC phreaking, where we're able to pick up like those unintentional transmissions. There is a talk by Melissa Elliott at DEF CON like many years ago, where she demoed like some of that stuff. Like, really interesting. Things like I said, microphones. This was really weird. I had a laptop and I was using SDR and I was tuning through the frequencies. And again, I was with a friend, and we saw this big signal somewhere on the spectrum. We're like, oh, okay, let's tune into that and see what it is. And I tuned in, and then I didn't hear anything. And I turned to them and I said something, and then as soon as I spoke, I heard that coming through the SDR. I was like, whoa, did we find a bug in the house or something? Like obviously super confused what was going on. It turns out that there was something in that room that was picking up our voices and transmitted them over the air. It turned out that it was actually the microphone in the laptop that was doing that. I don't know why. I'm not quite sure what was happening, but I suspect that the laptop was like, with the microphone in the laptop, was just receiving like voices or noises, and that sound is obviously still being transmitted along a small wire. And I imagine that the SDR was able to pick up that and tune into that and listen to that. Sometimes during smart meter assessments, we were able to use some of these devices, use this similar attack to again recover sensitive data like encryption keys and things like that. Another one, denial of service, obviously. So if we're able to transmit a signal that's strong enough, we'll be able to stop other devices from working. So this can obviously be used, kind of like, it can be quite dangerous, right? So imagine there's some kind of incident somewhere and you're jamming the signals, then first responders are not necessarily going to be able to be made aware of the incident, or if you jam phone signals and things like that. So this one, I think it can be fairly dangerous, and fairly easy to pull off as well. Fuzzing, I think, is one that probably should be explored a bit more, right? So with fuzzing, we're actually able to send data to two devices with the SDR. So imagine again like a mobile phone, and we want to be able to fuzz. We want to be able to find a vulnerability that lets us take over the phone, and we want to do it through the LTE chip, because obviously that's going to have lots of permissions. Well, what we could do with SDR is we could set up a fake base station that the phone connects to, and then what we'll do is just send it random data and see if we're able to cause a crash or find a vulnerability. People are doing that. There are some researchers that managed to DOS some phones by fuzzing it with some software called OpenBTS, which is an open base station, and they used the USRP to do that. So the phone connects to the base station just sends it like random data and does fuzzing that way. So I think this is quite a powerful technique that kind of would be good to see more people using. So we will try and do another demo. Let me switch over to my other screen. So this one, we're going to try and do maybe a simple replay attack. So I use different software for that. So close GQRX, and I use a software called GNU Radio. All right. GNU Radio is this. And what it lets us do is it lets us create kind of radio software with this kind of drag and drop interface. It generates Python in the the background, but yeah, it lets us do some kind of powerful things. So this is one that I created earlier. What I'm going to do is I'm going to disable some of these blocks here. And so the ones that are gray have been disabled. The ones that are not gray are enabled. So what we'll do is let's enable this. So the Osmocom source is the SDR, right? And the Qt GUI sync is just like a UI element. And what it's going to do, I've tuned in. You might be able to see here. I've tuned in to a certain frequency. Sorry to ask again. People can see my screen, right? I'm so I'm so worried that I might be talking and people can't see anything.
Yes, we can.
Okay. So I've tuned into a specific frequency, 433 megahertz, which you may be able to see in this Osmocom source. I've also set some certain details such as the sample rate, etc. And it's basically taking the data from the SDR and it's going to pass it to this UI sync. So the source and the sync. And if I hit play, assuming nothing goes wrong, we can see that. So it's tuned into a certain frequency and it's just displaying the data. Now, this is very similar to what we saw with GQRX, but it does not look as good. But we can see as an example, I have a wireless doorbell here. And if I push this button, you can see the data that went across the air, we're able to see with in the software. So to do a replay attack, we kind of want to do something with that data, right? We want to be able to save it and then replay it later. So what we'll do is I'm just going to disable, no, I suppose we can keep this open. But I have this other file sync, right? So we're taking the data from the SDR, it's going to go into the UI. It's also going to go into a file. So if I hit play on this and press the thing, we've now hopefully recorded that signal, right? So doing some of this, like when I learned about this stuff, it was super annoying because I had all these doorbells going off all the time. And I was like, dude, what are you doing? So now we kind of want to do the opposite, right? So if we disable the Osmocom source and the file sync, now we'll have a file source and you can see that the file here is the same that we saved into. So now rather than coming from the SDR into the file, we can go from the file into the SDR. We'll also keep the GUI sync here so we can see it. And you'll note that the frequency is the same, the sample rate is the same. So hopefully if I press play now, I don't know how to demonstrate that I'm not pushing the button. If I press play on this now, hopefully, there. So we saw that the signal is just being kind of repeated. And actually, if we keep it playing, like keep the SDR running, it's just going to keep putting that out in the air, causing the doorbell to continuously ring. So very basic like replay attack there. And of course, this is just a doorbell. The worst that will happen there is it gets kind of annoying, but you can do the same thing to to unlock cars, for example, or to open garage doors and things like that. So yeah, cool, that worked. I think so. How much time do we have left?
I think 20 more minutes.
Okay, awesome.
Yeah.
So let me go back to my.
I have a question before you go back.
Yeah.
So what's the Osmocom sync for? No,
so
QTGI sync. The QTGI sync.
So this one here. So I'm just going to disable this. This is just the GUI here, right? So yeah, exactly. There are lots of other different types of GUI things you can do. Now, this is of course the very basics of GNU Radio. You can build giant graphs that do all kinds of processing. So it will take the data, it will perform like filtering on it. It will do blah, blah, blah. And then eventually, you want to do something with that data, save it to a disk, demodulate it somehow. But this is just a good way to kind of see exactly what's going on. So
and you're using the HackRF.
This is the HackRF, yes. It works the exact same way with the RTL SDR as well. But what you'll see though is that, so you see in the HackRF, I'm looking at this whole range, and the actual data is just kind of a small part here. If you were to use the RTL SDR, because the sample rate is lower, you're only going to see a narrower band of this whole thing. So that might have to tune in a bit more. So one of the reasons why I like the SDR is because the HackRF is because it can see more at one time. You can be a little bit less accurate, I guess, if you're just doing a replay attack. You just kind of roughly tune into the right frequency and then it's fine. Where with the RTL SDR, you'll be a bit more accurate. Now,
and how did you narrow down to not cause the disruption with the other doorbells?
Sorry, say that again. How did I narrow it down to the frequency? Do you mean?
Yeah, like you said before, you got it to only sync to the specific doorbell. You were making other doorbells like go on and off every single time. So how did you overcome that difficulty?
So when I'm doing like this kind of research or learning these things, I make sure that I have my environment set up specifically. So I know that I want to capture one doorbell. I will have one doorbell around. By annoying before, I meant it was just the sound of that keep going on. And then obviously to find the frequency, I've got to press it, maybe use GQRX to tune through the different frequencies. So let me just try and show that quickly. So what I would be doing, for example, is pressing play on this, going through the frequencies, pressing it, and then just keep going through. And eventually, I got to I think it's 433. Is it 433? Yeah, there we go. Then eventually you get to it here. But yeah, I think that is kind of an important point to make, right? So what we saw here with the replay attack, very easy to do. However, it is not very accurate, right? I am just basically spraying data into the air. That is a legal gray area. These devices, they're not high powered at all, so there's no problem. But imagine that, for example, somebody did have a pacemaker in or something. And I hope this is less of a problem now, but imagine someone did, and it was like a radio connected one, and they happened to send a signal to that device as you were capturing this, and then you pressed play and did a replay attack, and now all of a sudden you're accidentally sending these other signals out into the air. So if people are playing with these kind of things, it is important to try and get a good test set up, so you don't have to worry about that. Things that I've played around in the past with is microwave ovens, so that they can be kind of good at shielding devices. Even aluminium paper, like tin foil, can be good at shielding devices as well. So when I am doing some things that is a bit more unknown, I do try to shield the best I can to limit it to what I'm impacting. Then the other way to do it is really you would want to have some filters in here that filter out all the noise, so you're only looking at your one signal. I hope that answers your question. Basically, just like if you want to do it properly, have filters in here, try and use test devices in a kind of safe area where you're not picking up other things.
Yeah, it answers the question. Thank you.
Okay, you're welcome. Okay, let me go back to slides. Okay, so we saw we did see some digital signals and we saw some analog signals. The analog ones are very easy to tune into, right? If someone's using a walkie-talkie or something like that, and you tune through with GQRX, you're able to just click on it, and usually you can listen to the conversation or something. With digital signals, though, it's a bit more difficult. We saw the doorbell data going across the air, and we did a replay attack. Now that works if we want to make that same doorbell ring, right? If we want to make another doorbell ring, though, Now, of course, this is I'm talking about doorbells here, but you know, what I basically mean is send our own data. Maybe it's maybe we've managed to capture the disable alarm code for our alarm, but we want to send to another alarm, or we want to just be able to to send our own data to devices. But in this case of the doorbell, we've captured the doorbell code that rings one doorbell, but if my neighbor's got the same doorbell, their doorbell isn't going to ring. How would we go about doing that? Well, we'd have to try and analyze the data that the doorbell key button is sending. So there are lots of different ways that data is sent over radio. There is the most simple one, I would say, is something called on-off keying. This really is where the signal is sent using pulses of, like, if it pulses, it's a 1. If it doesn't pulse, then it's a 0. And it will just basically do that. So an example, to send 0, 1, 0, 1, it would go no pulse, pulse, no pulse, pulse. So that's called on-off keying. The easiest one way to really be able to analyze. So that kind of looks like this, right? So this is some very outdated software. I will show you something a bit more modern in a little while. But this green part at the top, this is that waterfall chart that we were seeing in GQRX. And you can kind of see, hopefully anyway, that you can kind of see these dots, and that is basically the 1s and 0s going over the air. So where there is like a light green dot, that's where there's a stronger signal, and it goes 1, 0. And again, this waterfall is over time, so it plots it over time. So you can see that something is sending these 1s and 0s kind of over some kind of time period. The other common one that you tend to see, again, especially in like IoT devices and things like that, is something called FSK, which is frequency shift keying. And this is where data is encoded into the frequency that is being sent. So you might have like one frequency is a 1 and the other frequency is a 0, and it switches between those two frequencies. When I tuned in using GQRX a little while ago to show you where that paging data would be, I think that uses FSK. And if you look at the plot, you can kind of see that, and you can kind of hear it too. It changes between two different frequencies, and that tends to look a bit more like this. So again, I hope you can kind of see, but as it switches between two very close frequencies, but as it switches between two frequencies, it jumps between like a 1 and a 0 and a 1 and a 0. So by recording the data and analyzing it, we're able to understand how the data is being like encoded and sent, and then we can try and figure out how we can create our own data to send. So I'm going to just quickly try and demonstrate that. So again, let me switch back to this. So we saw the doorbell. Sorry, can people see this? Can people see the screen?
Yes.
Yeah,
yes,
we can see it.
Okay, good. I'm so paranoid about it. Because the thing is, people tend not to say. So I could be speaking for like 20 minutes and I realize that everyone thinks they're supposed to be looking at something else. But so here we have before we recorded from the SDR into this file, right? I just placed it in /tmp/record. So what we're gonna do is we're gonna use some other software called in Spectrum, right? Actually, so I'm just gonna switch back to the other thing for 1 second. Yeah, okay. Just I didn't want to accidentally share like something on my screen. I wasn't sure what it's going to show. Okay, so this is the file that I just recorded from the SDR. You'll also notice that it's almost 300 megabytes, right? That recording was what, 3 seconds long, something like that. if that, it was hardly any time, and it's already 300 megabytes. So that gives you the kind of idea. And also with the in GNU Radio, I was only recording at, I think it was 8 million samples a second. Sample rate, 8 million samples a second. The HackRF goes up to 20 million samples a second. But at 8 million samples a second, that records about 100 megabytes, I guess, every second. So this is not something that you can necessarily run for long periods of time, especially at those high sample rates. You're looking at gigabytes of data, hundreds of gigabytes of data maybe, which obviously becomes like very difficult to process. So you do want to try and reduce the sample rate as much as possible, whilst it's whilst still being able to do what you need to do with it. But let's say that we take this this file, so that's the one we recorded, and we open it in Spectrum. And if we scroll across, now this is like the waterfall plot, but it's on its side this time. So as I'm going right, that is kind of going over time basically. And you'll see at the moment there is no data. And then here is where I must, that's where I push the button and data gets transmitted. So what we want to be able to do is turn this into ones and zeros so that we can try to then like analyze it and see if we're able to maybe get another doorbell to ring or send some other kind of command. Now, in the past, this was very difficult, right? You'd either have to get a pen and paper and sit there and go like, okay, so this is probably a 1 and 0, 1 1 0 0, and write it down and hope that the data was not too complex or too difficult. So if I zoom out a little bit, you should see that. So when you press the doorbell, it sends this. And then if you look at it again, it waits and it sends the same thing. So this is the same data, and it waits and it sends it again. So that's because the doorbell, because it is kind of like a low cost thing, rather than having any kind of error checking or anything like that, it just basically sends the same, the same go beep command like multiple times. You would expect more complex systems to have maybe more of like a handshake or acknowledgement, or have some kind of error correction or something like that in it. But this doorbell doesn't. Just sends the same thing like over and over again. But to turn it into ones and zeros, yeah, like in the past, it was kind of complex. Within Spectrum, I like, because if we zoom in a little bit, we can find the signal. And it actually has this this like little selection thing here, and you can basically put it over the signal. Now obviously this is on-off keying, right? So we saw before with on-off keying, it just transmits like transmits for a 1 and doesn't transmit as a 0. And then so we can put this over the thing, and then if we just keep going up, it basically puts like a marker on every symbol. It does take a little bit of like moving around, but yeah, basically you keep doing this, and once you get it all, that's all of it. There we go. Now, no, there's a bit more. Yeah. Okay. So that is now like a little marker on every symbol, basically. Now I know that 37 is not divisible by 8. So probably want to add a few more at the end so that we know we're working with bytes. So it's probably this, right? And then you can just add amplitude plot, and then we say like this is where the signal is. And then down here we can do a threshold plot, and then here it's basically charted out the ones and zeros for us, and then we can extract symbols to stand it out, for example. And then if we look in the terminal, we see it's giving us the 1 0 1 1. And if we look, we have 1 1 0 1 1 0 0 1 0. So 1 0 1 1 0 0 1 0. Now this is the data that doorbell is sending. At this point, I would convert this to maybe to hex, and then we have basically the code that the doorbell sends out over radio to get this specific doorbell to ring. So what I would do at that point is I'd want to be able to send out maybe I would change the byte at the end to be like something. Maybe I'd increment it. Maybe I would keep incrementing it to get it to like send out different codes. Now with GNU Radio, as I showed it, we're only able with this kind of graph to send out the exact data we recorded, right? What we're not able to do is change that to send out different data. But within Spectrum, we know what that data should look like. I'm not going to convert it into hex here, but you can easily convert this into a hex string. Then if I wanted to change that, how would we go about sending it, right? What we could do is we could create a very complex GNU Radio graph that will take in a string of ones and zeros or string of bytes, and it would have to modulate it with FSK. It would have to do all kinds of stuff, and then eventually it would spit it out over the air, which is definitely one approach. The approach that I prefer, though, is to use this. If people can see, this is called a yardstick one. I won't be able to demo this now. This is a demo that I know isn't working because it still uses Python 2 for the libraries, and my laptop is Python 3, and I didn't want to risk breaking the other demos to update it. But with the yardstick one, this is more of like a software configurable radio. So for something like this doorbell, it works really well, but it won't work with everything. So what this basically does, you can tell this to transmit an FSK signal on this frequency and transmit these bytes, and then it will take care of the rest. So this allows me to just like, so I use this first kind of setup to figure out what data I might want to send, so what it looks like. Then I think, okay, well, I want to change this last byte. And then with a little bit of Python, I can control the yardstick one, and I can tell the yardstick one to send out, these specific bytes on a frequency that I select. And then that way you can get like other doorbells to ring or get some other commands. I hope that made sense without being able to demonstrate it. But my methodology really is to use GQRX to kind of do a high level analysis of like where the frequency is. And then I will use GNU Radio to do some very simple processing, maybe like saving data to disk, maybe doing some filtering, things like that. And then I will use in Spectrum to start to look at that data, understand exactly what the ones and zeros that are being sent are over the air. And then I will, if possible, I will then switch to the yardstick one where I'm able to just like tell it to transmit this string of bytes. And then I can have that becomes very easy then to just change what those bytes are and hopefully get get other commands to be sent, or maybe even do the fuzzing or something like that. So yeah, that's my general methodology. If it's a bit more complex, like if it's more of a complex protocol that isn't just doing something like FSK or OOK, then I would need to do a bit more in GNU Radio. There is some other software called Universal Radio Hacker that also helps you to recover this string of bytes. That's actually a bit more automated. You don't need to like select them. You just give it the file, tell it some details, and it will try and spit out the bytes that it's managed to detect from that radio file. But that for something very simple like this, like doorbell command, that works really well. But for more of like a manual thing, I tended to do it this way, or for more of like a complex signal. Okay. Screen this. Okay, how are we for time?
It's almost up, but we can still go on.
I mean, that's basically it. The rest of it, really, the rest of the talk is just some information about, again, some like common protocols. I suppose if people are okay, I'll spend a couple of minutes just going through this, but it won't take very long at all. So phone hacking, right? Phone hacking is always something that people are interested in. And when it's in the news, though, it's kind of lame, in my opinion. This was in the UK news years ago, where people were talking about phone hacking when really it was just like guessing like pins for voicemail. But yeah, everyone's talking about phone hacking. But actual phone hacking, I think, is more interesting. So this is with GSM, a very old protocol now, but it's still in use in a lot of places. The way that GSM tends to work is the base station tells the handset that it should be encrypted, and then the handset does encryption of traffic. If we're able to capture that data, right, using something like the with GNU Radio, saving the data to this, for example, we then have all that encrypted data. There are ways to crack that, right? So you can crack that encryption, especially with today's like hardware and stuff. And then you're able to like listen into those signals. What you can also, I mean, so there are some countries as well that do forbid encryption on GSM, so you can like that becomes even easier to tune into and to listen into. And also, what you can do is you can pretend to be a base station. So what you can do is you can set up your laptop with the SDR and tell the SDR to act as a base station. And phones, they will connect to whatever base station is in the area that is the strongest signal. So if your signal is stronger than like the legitimate base station, the phone will connect to you, and then you can, if you want to, you can relay that phone call if you want, over like over the internet, over VoIP or something. So the victim is not necessarily going to know that's happening. So yeah, I mean, there are lots of attacks here. Interestingly, I'm not sure if this is still the case, but it was the case that phones will, even if they're on like better protocols like LTE or 5G, they will still prefer older protocols if the signal is stronger. And you'll see this, right? Like as you might be walking around, your phone jumps between different base stations, whichever one is the strongest. If it can't get a 4G signal, it will jump back down to something else, to GSM maybe, if that's what's available. So even if a phone is on 4G, which is a lot harder to break, you can still, if you're able to provide a stronger signal, the phone still may connect to you. And law enforcement use these kind of techniques. So GSM is vulnerable to like some of these attacks that we looked at earlier, as well as some crypto attacks because the crypto is broken. So Bluetooth, Bluetooth low energy, Bluetooth Smart, it was originally called, but Bluetooth low energy, used for lots of things like door locks, like iPhones have access to it and things like that. Like people might have seen the what are they called, the Apple tags or something, I'm not sure. I think they're using Bluetooth low energy. By tuning in with some of these devices, we're again able to perform certain attacks. I will just skip the details of some of these attacks about how Bluetooth does like frequency hopping and stuff. But basically, there are some pairing. There are some some key generation issues. So you can with SDR in the right scenarios, you're able to access the long-term key and then decrypt some of the data. The encryption in it is actually pretty good. It's just the pairing mechanism can be a bit broken in some cases. If you're doing something like out of bounds pairing, so you're using NFC to exchange those keys, you might have seen it where you can like touch your headphones to your laptop. I've seen people do where it will then connect to Bluetooth. That tends to be fine. But when it's in just works mode, it can be a bit more broken. So again, some attacks, especially around the poor key exchange. So again, the crypto is actually good, but the key exchange can be a bit broken. There are some tools specifically for Bluetooth hacking. I've got one actually over there, but Ubertooth is probably the most well known. And I mentioned Zigbee before. I like this one because it's a good example of a specific attack. So when you add a new Zigbee node to a network, so Zigbee is used for like home automation and in factories and things like that. When you connect a new device to the network, the traffic is encrypted, but it gets a copy of the key, right? So there are a couple of attacks you can do there. If you're able to get access to the device afterwards, let's say that it breaks, they throw it away, you may be able to dump the key from the firmware. Or if you pretend to be a like a malicious node, it might just even give you the key. Then all of a sudden you're able to communicate with the network. Now this isn't completely passive because you do need to like join the network to get the key. So if you're passively listening, it's fine. But then if you're doing more of an active attack, more of a problem. I've not kept up to date with a lot of the Zigbee attacks. I know that a lot of work was being done into it a few years back. I imagine it's gone even further than this very, very simple example that I have here. So if you are interested in Zigbee, I know there's like specialist tools and hardware for it. So yeah, again, some attacks plus poor key exchange. So yeah, we've spoken about, a few things here. I hope that there was some new information. I know that people did say that they have used or played with SDR. Hope there was some new stuff here. A lot of people often think that radio hacking is very difficult, and it was very difficult in the beginning, very expensive as well. Then it became cheaper, but still very, very difficult. Now I kind of feel like it's moved to where it is significantly easier. People are using these things, even on CTFs. They're so easy and accessible that I've run CTFs where people are hacking radio things, and a few years back I couldn't even imagine doing something like this. So yeah, really, really cool. I think SDR really kind of, back in the day for radio hacking, you'd have equipment that was a bit more like this, right? Lots of devices, lots of specialist radio equipment, whereas now you can get away with just having something like the HackRF and the laptop. And that is it. That's all I have to say about SDR. Did any questions come up in chat?
Yes, I believe a few questions come up.
Okay, I'm just reading through them now. Somebody. So protections against tapping into the aircraft location. There isn't. So somebody just asked about when I was talking about the aircraft stuff, any protections against that kind of thing, and there isn't. Anyone can just tune in and see that. Which is kind of like interesting because you can, if you, as an attacker, you can just kind of plot that. There's not tons and tons you can do with that data. It's just kind of, again, like the location, the longitude, latitude, the flight number, things like that. Now, what I've always been curious about, I have been told it wouldn't work. I don't know the details, but I know that aircraft, they do use that data for certain things, right? So I think it's displayed to the pilots, and the autopilot will change based on where other planes in the area are. So I do wonder what would happen if you had an SDR, and instead of just receiving that data, if you were to transmit that data, and you tell a plane that there's another plane next to it. I've always been curious about that, but I'm definitely not brave enough to try that. That would be a very, very bad idea. Oh yeah, here we go. Someone here says ADSB sent in clear text. So yeah. So yeah, somebody says about displaying them. If anyone wants to message me, I probably have like an old video where I can set up a demo of the ADSB stuff, which is the aircraft thing. But it's a very like easy one to do yourself if you can get hold of something like the RTL SDR. Demo of BTS frequency sniffing. I don't have that set up, unfortunately. So with the RTL SDR, you can do some GSM sniffing. People call it like IMSI catching. I don't, it's not quite correct with the terminology when they say that. But if you Google like IMSI catching with the RTL SDR, then you'll be able to pick up some things. It's more like some of the metadata, like some of the like, you won't actually see like the calls or anything, but you'll see some metadata. It could be interesting. And then do we still use the same tools? In relation to what? So Collins asked, do we still use the same tools? Potentially. depends same as what. Maybe that wasn't a question to me, but maybe that was related to something else. With RC planes, so with RC planes, you'd be able to take control of them potentially, but not necessarily like see where they are. Obviously, they're not using ADSB. There are, so someone asked, are there any security measures? So for some protocols, they do have security built in. You know, they will be able to, you know, again, if they're using encryption with good key exchange, you know, that's going to be fine. More complex protocols like even Wi-Fi, you know, that is a more complex protocol that wouldn't necessarily be attacked by an SDR, but there may be Wi-Fi attacks against that. You know, maybe you can get the device to connect to a malicious access point and send it commands that way, or something like that. What's my take on IMSI captures? I think they're super cool. I've always wanted to do a bit more work with them, but it can be a bit difficult just in terms of legality and having a good like test up. What I don't want to do is have people connecting to accidentally connecting to my devices, because that would obviously be a big problem. But I think they're really cool. And again, law enforcement, you know, are using them a lot. So yeah, there's something to keep in mind. It's not always difficult to set up. Then HackRF gets GSM frequencies. Yes. So HackRF, as I mentioned before, goes, well, it went from 24 megahertz to 6 gigahertz. The range now is actually a bit more. The one you might have seen in GKRX, it went, I think, as low as like 3 or 4 megahertz, but there are some limitations when you get down that low. GSM, I think, uses 900 megahertz, so well within the range of the HackRF and even the RTL SDR. But the RTL SDR is, again, because the sample rate is so small, you're not going to be able to capture enough data, but you can view some parts. There are some tools that you can use to view certain things. So it might be worth just, you know, playing around with this, and if you are enjoying it, upgrading something like the HackRF, or even more if you want. I bought the HackRF like a few years back. Actually, when was it? I mean, a long time ago, actually. So you know, I'm sure there are other devices now that are maybe I'd recommend if I was able to use them. A friend was telling me about one a bit cheaper than HackRF, but a bit more limited in terms of sample rate as well. So yeah, I mean, definitely explore around, and you probably get some. I'm sure you can. I'm pretty confident that you can get devices that will transmit for less than £100. And again, I can't convert that to any other currency, but yeah, it's definitely becoming a lot cheaper than it was. Are there any other questions? I guess that means no.
Okay. Yeah, so if you guys have any other questions, you can always connect with Jay. You can follow him on Twitter. You can join the Manchester Grey Hat Slack. Jay, where else can we find you?
Honestly, Twitter is probably the best place. And if anyone wants to reach out, obviously feel free. I'm always happy to answer questions, to help people get set up with things. You know, if people want advice or whatever. Yeah, usually Twitter or Manchester Grey Hats. If you search Manchester Grey Hats, you'll find our website, links to our Slack. If the links have expired, let me know. I'll send over new ones as well. I also have a podcast as part of Manchester Grey Hats, if people are interested. We've not released an episode in a while. It's kind of funny, isn't it? I think everyone over lockdown started a podcast, and that includes Manchester Grey Hats. So we will be putting out a few more things soon. And on Manchester Grey Hats, we also have a YouTube channel where I do try to create videos, but giant list of things that I plan to do. I can only get through it so fast. If people do want to help as well, you know, Manchester Grey Hats is a community group. It's named Manchester Grey Hats because that's where we started, but you know, we do have members from like all over. If people just want to get involved with projects or help us out with things or whatever, you know, it'd be awesome to get more people involved.
Awesome. Yeah, Jay, we're definitely looking forward to our community members being a part of your community as well.
Awesome.
And thank you so much for joining us for today's session. We have definitely learned a lot, and we look forward to more tutorials, more stuff from you, the podcast, and all the other stuff you're doing. We look forward to that. And yeah, thank you for joining us. And thank you everyone for joining the session as well. And we will see you. Yeah, Jay has posted in the chat the Twitter for Manchester Grey Hat, so you can follow that as well. Yeah, thanks everyone, and
Awesome.
have a good night.
Thank you.
Right.
I will just stay around if anyone wants to ask any questions, but maybe didn't want it being streamed.
Jay,
Yes.
I'm curious. How did you get into security?
Oh, you know what? People ask me that a lot, and I wish I had a good answer. I don't know. It just happened. One day I realized that I was just kind of doing security stuff. I think when I was a kid, I was in school. My friends, we were playing with computers, and kind of hacking the school and stuff. We were really lucky. One of the IT admins there was very he let us do it. We didn't get in trouble for doing it. And he basically said, as long as you don't break anything, as long as you report things that you find, you can do what you want. And so we just kind of learned it that way. And then I just kind of followed that path. I didn't really even know that like security was a job or anything like that. I was just really interested in computers. And then and then after a little while I started working as a pen tester. So yeah, I wish there was a good story, like I don't know, like in some of the films or whatever, but no, I was just a nerdy kid that spent too much time on computers.
Oh, that's interesting. And reversing on mobile apps, how did you get into it?
So that one, I was just kind of pushed into. Before we go into that, I think we are still being streamed on